This is a short presentation of a single scenario where a formation of 4 multi-rotors carrying a sling load is exposed to an infinite stationary horizontal vortex as part of my research. Let's begin with a brief discussion. In this example, you can see two simulation models of the same system, where they differ only in their physical implementation of the rotor's aerodynamics. The left simulation model, denoted as the simplified model, or also the reference model, uses the aerodynamic model of the rotor of the control design itself as its physical implementation model. This model assumes that the generated thrust and torque are only a function of the rotor's rotational speed, as you can see in those equations. The coefficient Ct and Cq are constant and usually evaluated through lab experiments. From literature review, we saw that this is a common approach used by many control designers, meaning utilizing this model for the control design and for the physical model alike. In the right simulation model, termed as the more realistic model, the physical aerodynamic model of the rotor was developed using the momentum and blade element theories. In short, the forces and moments generated by the rotors are now also dependent on the local air inflow. Furthermore, the model also computes the generated side force and drag. So those were the simulation models, and now let's explain the presentation that we see before. On the left of the screen, you can see the trajectory overview of the two simulation models. It is a straight trajectory where the system tries to fly at a constant speed of 5 meters per second. Above the trajectory, you can see the vortex profile, which consists of a contour wind intensity and the wind direction. On the right of the screen, you have a closer look on the system of the two simulation models, with a closer look on the wind direction and the intensity of each system component. Okay, so now that we have a better understanding of this presentation, let's start. Moving fast forward till the system is near the vortex axis, or also known the eye. So when the wind system passes the vortex axis, the wind direction changes rapidly, triggering the system response. The realistic model then slowly loses attitude stability till it reaches control saturation, and then destabilizes completely, ending with a collision between the multi-rotors. On the other hand, the simplified model response to the vortex gradient is insignificant, and you can barely see it. The result scenario is semi-summarized in the following figure, which displays the trajectory error. The blue line, representing the simplified model, has a minimal deviation from the desired trajectory, whereas the realistic model, the orange line, deviates by an order of magnitude from the desired trajectory till it fails and the multi-rotor collides. In this example, we demonstrated the inadequacy of the commonly used simplified aerodynamic model of the rotor when faced with turbulent wind conditions found in urban areas. Thank you very much.